One of the things that we love to do with derivatives is to find the equation of a tangent line, as you can see on example 6. Equation of a tangent line to the graph of f of x equaling the cosecant of x at specifically x equals pi over 4. So what two pieces of information do you need in order to write the equation of a tangent line? One, you need a point. We have the x value. We're going to have to plug that back in to the function so we can have the y value. And we also need the slope. How do I get the slope? By taking the derivative. And you know what? We have the derivative rule for cosecant. It's right over here. Derivative of cosecant is negative cosecant cotangent. Okay, so let's get started. Okay, so let's first find the y-coordinate here. So f of pi over 4 is equal to cosecant of pi over 4. And I don't know about you, but I don't think in terms of cosecant. So instead, I'm going to go with 1 over sine of pi over 4. And maybe right over here, draw myself a unit circle. Pi over 4. Hey, that one is the one of 45 degrees one, right? It's the 45, 45, 90 right triangle. And the x and the y coordinate are both square root of 2 over 2. And I don't know whether or not you remember or not, but the reason why it's square root of 2 over 2 is because it came from 1 divided by the square root of 2. I'm just saying. And then we rationalize it. Because if you think of it like that, and then I go over here and I put 1 over the square root of 2, I could very easily see that it's supposed to be the square root of 2. Could you have gotten it from this? Sure, you could have. Maybe would have taken maybe an extra step or something like that. But we have the coordinate pi over 4 for our x coordinate, square root of 2 for our y coordinate. Now then, let's find the derivative, shall we? So f prime of x is equal to, it is a cofunction, so it's going to be negative cosecant cotangent. Cosecant pi over 4 and cotangent pi over 4. Why did I plug in a pi over 4? Got ahead of myself. I got way ahead of myself. There should be x's first, and then I'm supposed to plug in the pi over 4. Okay. Negative cosecant pi over 4 and cotangent pi over 4. All right, I'm pretty sure we just found cosecant of pi over 4. That's square root of 2 business. I got negative square root of 2. How about the cotangent of pi over 4? So pi over 4s are super special for both sines and cosines. Those things are just equal to 1. So let's go ahead and multiply this by 1 to get negative square root of 2. All right, and then we want to put both of these pieces of information together in order to write the equation of our tangent line, knowing that that is the tangent slope. And putting it together in point slope form, y minus my y coordinate, square root of 2, is equal to my slope, negative square root of 2 times x minus pi over 4. And there is nothing wrong at all with leaving your answer like that, of course. Unless, multiple choice question asks you to put it in a different form, and then I have to use some algebra to simplify it or rearrange it in some kind of way. You wanna? Why not? Let's see. Y minus the square root of 2 is equal to, let's distribute here. I'd get a negative square root of 2x, or maybe I put the x up front so it's not confusing. And then negative times negative is positive pi root 2 over 4. Okay, and then, then we'd have to add this guy over. Y is equal to negative. Do we want to put the x up front just so it's not confusing? How about a 2 inside that? Okay, and whenever I add this over, it is pi root 2 over 4, and then plus root 2. And you look down at your answer choices, and maybe this looks sort of like the one of them that they have, and maybe sort of it doesn't, because maybe what they decided to do is factor out a square root of 2, maybe from the whole thing, or maybe just from the y-intercept. I don't know. Who knows? Negative x root 2 plus a root 2 times pi over 4 plus 1. Who knows? Maybe that's the way it looks. I don't know. Any of those things would work. And, you know, I have no idea. Maybe they even factored out that 1/4. I don't think like they do. It's not my job. That's your job. All right, let's look at the next one. Let f of x equal to secant x divided by 1 plus tangent x. For what values of x does the graph of f have a horizontal tangent line? This is a super popular question type on the AP exam. Horizontal tangent lines. Why do I care about horizontal tangent lines? Because that's where some super special things happen, like those relative mins and maxes. It's not the only thing, but it is something that traditionally happens at those zero sloped lines or tangent lines. Oh, I'll come over here so we have plenty of room. What color we got? We got green again. All right, notice we have a quotient. So since we have a quotient, we're going to have to use quotient rule. Take its derivative. F prime of x is equal to derivative of the top. What is the derivative of secant? It's secant tangent. Times the bottom. 1 plus tangent x. Okay. And am I going to have enough room? Here. Let's preemptively just bring this down here. There we go. Minus, I think I said plus, but minus the top, secant x, times the derivative of the bottom, and the derivative of the bottom is secant squared. There's a whole bunch of secants in there. All of this over 1 plus tangent x quantity squared. All right, and then maybe what I got to do is simplify this in some kind of way, because I need to set it equal to 0. Horizontal tangent lines, of course, mean slope is equal to 0, which means f prime of x is equal to 0. And you know what? If this was on a free response question and you had this on your paper, more than likely that qualifies you for a point. Just saying, get in the habit of doing it. All right, so what can we do? Can we cancel out this in one of these? Oh, please tell me we can, but we can't. And why can't we? Because it's not a common factor across the top. If it was, then we could cancel it, but it's not. But there is a common factor of secant. Maybe I pull that out. And then I would have bracket tangent x, 1 plus tangent x, and then I guess minus secant squared x? Oh yeah, close a bracket with a parenthesis. 1 plus tangent x. That doesn't look that much prettier, but maybe something nice will happen whenever I distribute this tangent through here, and I'm going to have secant squared and a tangent squared. That sounds Pythagorean if you ask me. Secant x times, I'd have tan x plus tangent squared x minus secant squared x. And then, you know, copy and paste the bottom 14,000 times. Now, why did I do that? The reason why I did that is because I'm going to use an identity to kind of replace this. There's no way I want to solve this kind of thing, setting this thing equal to 0 and, you know, trying to solve this trig equation when there's all of these different trig functions in there. No. So I'm going to use a trig identity. And the trig identity that I'm going to use is just the good old-fashioned sine and cosine one. So it's the Pythagorean identity, sine x, or sine squared x, plus cosine squared x is equal to 1. That's the only one you really need to have memorized, because you can get the other ones from this. Because watch what happens. Watch what happens, my friend, if we divide everything by sine squared. Can't we just divide everything by sine squared? Yeah, as long as I do the same thing on both sides. And I did that because sine squared divided by sine squared is 1. Cosine squared divided by sine squared is equal to cotangent squared. And then 1 over sine squared is equal to cosecant? No, yes, cosecant squared. Yeah, that doesn't look like what I wanted, right? I got the exact opposite. All right, I'm back to the drawing board. No worries, no worries. Made a fatal error, but I can fix that fatal error real fast. So I wasn't supposed to divide by sine x. I should have divided by cosine. Cosine squared x. Cosine squared x. And one more. Okay, what's sine squared over cosine squared? That's tangent squared. This is looking better. Plus 1 is equal to 1 over cosine squared is secant squared x. There we go. And now look at what we have. We have tangent minus secant. Tangent squared minus secant. I can get that from this very easily if I just subtract this guy over and add this guy over. I mean, that's not all I could do. I could just take out the secant squared right there and then replace it with that if I wanted to, but I don't. Instead, I'm going to rewrite this as tan squared x minus secant squared x to be equal to -1. So I'm just going to replace this right there. That was a terrible color to choose. How about this one? Okay, I'm going to replace this with -1. Secant x times tan x minus 1. I guess I don't need brackets anymore. 1 plus tan x squared. All right, kind of lost track of what the heck we were doing for this one. Horizontal tangent lines. That's right. We want this derivative to be equal to 0. How do you have a fraction equal to 0? You only have a fraction equal to 0 when top equals 0, but the bottom does not equal 0. Because if they're both equal to 0, you have the indeterminate form 0 over 0, which is messy. So instead, we just want the top to equal 0, bottom to be something else, right? And, you know, the whole reason why algebraically is because you would multiply both sides by 1 plus tangent squared x, or tangent x, quantity squared. Over here, it's multiplied times 0, and you're only left with the top. We've got secant x times tan x minus 1, and we want to make that equal to 0. Now, we'll check this bottom part here after we have our answers just to verify that we don't get a 0 over 0. And now we got a product. We're going to use the zero product property, just like we do with quadratics. I got a product of two things multiplying up to 0, so that means that maybe secant x is equal to 0, or maybe tangent x minus 1 equals 0. Let's do them both. Secant x equals 0, or tan x minus 1 equals 0. Hey, where is, oh yeah, wait, secant is 1 over cosine x equals 0. Can that ever happen? Can 1 over cosine x ever be equal to 0? It sure cannot. So this one is not happening, which means it must be this thing over here on the other side. Is green. Tan x is equal to 1. Where's tangent equal to 1? Let's draw a unit circle. Tangent is equal to 1 here at pi over 4, or also over here. So how far do I have to go to get to the next one? The period of tangent is pi, not 2 pi like it is for sine and cosine. So this one is 1/4, 2/4, 3/4, 4/4, 5/4, 5 pi over 4. And then I can get another one if I just keep going another pi. Another pi. So one of the ways to write this is that x is equal to pi over 4. Here's one of the answers. And that's the answer that you would get if back here on this equation that you were just, if you took the arctangent of both sides, you'd only get that answer. But this is going to hit it an infinite number of times. And to get any of the other ones, you just add the period to it, or a multiple of the period, like in pi, where n is some sort of integer there. All right, let's take a look at the graph of this and see how that plays out. All right, so in blue, you have the graph of secant x over 1 plus tangent x, and then you can see that we have some horizontal tangent lines here. And where do they happen? They happen at, apparently, a pi over 4, and then over here we have another one at, say, Was it 5 pi over 4? Something like that. Okay, so that'll just about do it. I think this video is long enough.